last linear algebra class. The previous one was just some discussion. And the first reference, well, basically, let's mention only these two reference, because you can look at any reference that you like, but we will mainly use these two. Okay. R10 is quite good, whereas from Hopper course we will cover the linear functions, but mainly we will look at R10. And what we are going to cover, well, at first, this is a syllabus, and more or less we'll stick to this. So the first is system of linear equations. Well, it's like A is equal to B, and matrices and determinants. So this part has already been covered in your previous, in the previous semester by the teacher. The second one is vector spaces. Linear independence. Basis and dimension. What else is there? Linear transformations. Rank-Lamp theorem. And characteristic polynomial or eigenvalues and eigenvectors of a linear operator. Algebraic and geometric multiplicities of eigenvalues. And diagonalization. Okay. And then comes inner product spaces. Okay. So let's use this board. So 4 is no, before even inner product spaces, there's a particular kind of linear transformation. It is called linear functionals, the simplest kind of linear transformations, with which we'll spend some time. Dual spaces. And annihilators. And the fifth is inner product spaces, orthogonal basis, Graf-Smith process, what else? Unitary and Hamiltonian matrices. And finally, the cherry on the top, it is the spectral theorem for normal operators. Yeah, so this syllabus looks sort of ambitious. We'll see how far we could cover. Okay. Ideally, we should cover up to this, at least the statement of this theorem, if not the proof. Because I'm saying this obvious because we cover this every year. But this year, the lecture hours is reduced by 1 hour. Well, we are also reducing our syllabus by just removing this one. Okay. So we begin from here and we plan to end up here. Nevertheless, I hope at least you recall the basics from this part which has been covered in the previous semester. So linear algebra is not just this solving system of linear equations. You see, then the syllabus would stop here. Right? So what are these? The rest, it's the study of solution spaces. So linear algebra is studying the structure of the solution spaces of such equations. More generally, algebra is the study of structure. Okay. So in that sense, in particular, linear algebra is studying linear structures, okay? Linearly defined structures. So in some sense, then the work of a linear algebraist is similar to the work of an architect or an orthopedic. Okay. But you won't see a vector space coming to you saying that I have a broken basis. Okay. Would you please fix it? And then he will say, well, how did you break it? Okay, let's see. If we extend it slowly, is it painful? Or you have broken it badly? Maybe we can just change it. Okay? And then you give a course of physiotherapy to the vector space. Okay, after class 12. Okay, you don't do this generally. Okay, so how do you study? How do you begin with vector spaces? We define vector spaces over a field. And before we define a field, we should define the more basic structures. Okay? So in the last class, we started with binary operations, right? So let's recall what they were. Okay. So S cross S is so S is a set. And from S cross S to S, there's a way of combining two elements to some other element of S. For example, consider this set of natural numbers. I hope this notation for natural numbers is known to all of you. That is, n is just a set of 1, 2, 3. So this one plus on n. In which you add two natural numbers to get another natural number, right? So this is indeed a binary operation, plus on n. How about this one? N with multiplication, it's also fine, right? How about this? No. Right? Because if you subtract two natural numbers, you get some negative integer, which is not in the system of natural numbers. Or you get 0, which we also exclude from natural numbers. That is, in mathematics and computer science, they add it. They start with 0. So n, it's just a difference of concepts. Difference of notations. It's otherwise fine. We also denote that with 0, but with n 0 here. Okay. Or maybe we just write and say that would mean this, you mean 0. How about this one? Right. So this is not. Neither this nor this is a binary operation on the set n. Okay. Set of natural numbers. Okay. So next comes the definition of groups. It's a group is a set with a binary operation defined on this. Okay. So a set G with a binary operation star on G such that these two things are satisfied. One is associativity, that is A star, B star, C. It doesn't matter which star you do first, B star C or A star B, it's the same. That's associativity. And then identity. Given an element A, there exists, not given an element A, there exists some identity element of this group G, so that A star Ig is equal to Ig star A equal to A for all A in G. And then there is inverse. Okay. So this is some element of the group G with which you compose A to get back A. For example, in the set of integers, the identity is 0. This is just some operation on this set, right? So this set could be Z, for example. This operation could be plus. Z is the set of all integers. So this is the set of integers. With this we denoted just the natural numbers, and this is a set of other integers for us. So inverse. Okay, in Z, 0 is the identity element, and IZ under the operation plus is 0. Okay? And then that means if you add A with 0, you just get A back. Okay? Similarly, not similarly, the inverse in Z is like, well, let's first write down here what inverse means. For each A in G, there exists B in G such that A star B is equal to B star A equal to the identity element of G. Okay? So in particular, if you take Z and take some element minus A, given A, you have minus A there, which you add with A to get 0, the identity. So therefore, all these conditions are satisfied by Z. And can you give another example of a group except Z? Yes?
So the symmetries of a triangle.
Yes, Z. So that's yeah.
How is from this definition? How is integer binary groups? Because
Yes.
0 exists in the integers, and
Yes.
0 doesn't have a multiplicative inverse.
Yeah, but we are not talking about. So we said that this could be any operation on the group. Okay. So a group is having only a single operation. We are considering the integers just with addition.
Oh, sorry, I confused with field.
Okay. Or maybe some concept in between groups and field. We'll see that. So just a minute. Well, fine, yeah.
Sir, so can we construct integers or natural number with just multiplication on it?
Integers or natural numbers, just multiplication on it. We'll do that, okay? But not immediately after the definition of
So
group.
we can do that.
We can do that, of course.
But in the case of integers, and in some books it was written for natural numbers as well, that there exists an element there exists 0 in it.
Okay. Here in
Yeah,
we said that for us this set will be just 1, 2, 3, etc. Okay, and there are, well, in some, as you mentioned, for example, for computer scientists, they will start with 0 from here. For that, we use just maybe n0. Okay, or more authentically, this one, z with greater than 0, greater than equal to 0. So we could specify any lower bound here or any upper bound here, or you could write that z a b. You have all the integers between this in this interval. Okay. So you write the superset and the condition here to let people understand that exactly which integers you are talking about. So this will just be z intersection AB for us. Okay, and this one for us will always denote the numbers starting from 1, 2, 3, etc. We don't include 0 in it. It's our convention. Okay, so yeah, to respond to Fahim, I'll just write down a few sets here. It's a set of integers, okay, and set of polynomials, matrices, functions, but the domain should be specified. So functions like, not domain, the range, okay. Integer valued functions, or similarly the coefficients of the polynomial should also be specified, and from which place you are taking the coefficients of polynomials. Ideal value function or rational value function or real value function. Or maybe continuous functions from R to R, or differentiable functions from R to R, and so on. Okay. So all these sets have an underlying similarity in their structure. Okay. So we have to see what is the similarity. We're coming back to that in a moment.
Sir?
Yes?
Should not it be invertible? Should not we specify invertible square matrices?
Invertible square matrices? No, we are not defining it. We are just saying that set of matrices over, say set of all real matrices or set of all complex matrices.
Okay. So to form a group, I think.
I'm not saying that this is group. Okay. This is some other algebraic structure.
Okay.
To which we come soon. Okay? But nevertheless, groups are like the basic building block of structures. Okay? But even there are things which are more basic, and let's mention that in a moment. Oh, by the way, in the previous class we saw abelian groups as well. So abelian groups just means that this one is commutative. That means you don't have to write a star b times b star equal to infinity. It's fine if you just write a star b equal to infinity. So abelian groups a group G such that this operation star is commutative. Okay. And this concept of abelian group, we are going to use it over and over again because a vector space, which we will define soon, is an abelian group. Now, we said that there are structures which are more basic. For example, take a group and consider only the first assumption, that is the associativity. Suppose we don't have the rest. So that would be called a semigroup. Set G with an associative binary operation star. Okay. Just the first axiom associativity. Then suppose we have these two axioms and we call that a monoid. Okay. Can I write the left board out? The groups? This one? So to call it a monoid, we just wipe out the last condition. And then it's a monoid. Okay. For example, this one is a monoid. Okay. Wait a minute. Is it a monoid? N star. Yes, of course. Because multiply anything with 1, you get that number back. Whereas there is no identity. So n is there, but 1 by n is not there. And for a semigroup, throw away that 1 from there. Okay. Start from 2. For a semigroup, just consider z greater than or equal to 2. You throw away 1, and the rest of the things you still have multiplication defined on that, but now no identity elements there. Right? Okay. So we see that still now we saw what is a group, what is a semigroup, what is a monoid, and what is an abelian group. If any of you are lagging behind, please tell me, we can repeat the thing. Yeah. Or if you don't see an example of any of this, if it is not clear, just let me know. Don't just sit back, because what will happen soon is that a set of people will interact with me, will talk with me, and I will answer to them. And in the feedbacks, it's often written that you are focused on a particular group of students. I'm not. I'm just getting acquainted with you. So people who communicate with me, I answer to them. But people who prefer to not speak and not let me understand where they are having difficulty, how can I fathom how much they have understood and how much they haven't? So please speak up when you have any difficulty in the class. Yes, yes.
Can you again repeat that example for semigroup?
A semigroup? Yes. So what is a semigroup? It's a set of it's a set G such that you have an operation defined on this, and it is associative. That is, for a semigroup, we do not care whether there exists identity or inverse. Okay? For example, a group is of course a semigroup. A group is a little bit better than semigroup, but it's at least a semigroup, right? So that means it has the operation, the binary operation star defined on it, and that is associative. Okay, so take any example of a group that serves as an example of a semigroup. But nevertheless, this one, what we mean by set greater than or equal to 2, this is just the set of integers 2, 3, 4, etc. Okay, and if you multiply any of them, you get something back in the set. So it is closed under multiplication. Okay? And that multiplication is of course associative. That is, it doesn't matter whether you multiply 2 times 3 first and multiply 5 after that, or whether you multiply 3 and 5 first and multiply 2 after that. Okay? Yes, if you have a doubt, it's better to speak to me. Excuse me. Yeah, rather than asking your friend, it's better to ask me, because otherwise there's a crosstalk in the class.
Is monoid a semigroup?
A monoid?
Is monoid a semigroup?
Of course, yes. Because it is satisfying this semigroup axiom, right? So the semigroup has no other axiom except the axiom of associativity. Yes, please.
So can we just say that a group is a superset of semigroup and monoid?
A superset? No, a superstructure you can say. Because it's a kind of a structure, an algebraic structure, and over this you are putting no. you cannot say actually it's a superstructure. Rather, you can say that a semigroup is a superstructure of a group, because inside semigroup you are already, so groups, the set of groups are sitting inside semigroups, or the set of monoids are sitting inside the set of semigroups. So it's like what I draw. So suppose this is a set of semigroups, and then there sits inside the set of monoids, and inside that sits the set of groups. Okay. And even inside that sits abelian groups. Okay. Okay, now let's look at the set which we have written there. Are they satisfying the concepts of groups, monoids, semigroups, and what can you tell about their structure in general? In all of these things, yeah.
So you haven't defined the binary operation yet for any of them.
What?
The binary operation you haven't defined for any of them. We will comment on.
On this, yeah. Actually, the thing is that there are more than one binary operations on them. In all of them. Like you can multiply integers, you can multiply polynomials as well. Of course, you can add the things in there. If you add two continuous functions, you have already done as this one? No, it's a, or you are studying as, okay. So later you will see that you can add continuous functions and get continuous function. You can multiply continuous function and get continuous function as well. About differentiability, the same thing happens. Okay. So, for handling structures like this, we introduce a new concept. So here you can write one ring to rule them all. Okay. So it's a concept of ring. It's not Tolkien's ring, but ring in algebra. So a ring is a group, of course. Yeah, an abelian group. R plus with a further operation star such that
So is that binary?
yeah, another binary operation star such that R under this binary operation is a monoid. Okay, that means you can, R plus is a group is an abelian group in the usual sense, whereas this one will have an identity element. It's called actually a commutative ring with identity. We'll just call it a ring. Okay, and all our rings will have identity. So, and this will be R star is will be a monoid. That means the things in R may not have a multiplicative inverse with respect to star. Okay? So it has two operations. For example, take any of these things here, integers, polynomials, matrices, you can add them, you can also multiply them. Okay? But someone asks whether, asked earlier whether we define the matrices with which has only inverse, I mean all the inverses. All the matrices with inverses, we do not in general for while we are defining ring. Okay? We take all the, say, okay, maybe square matrices here. So n cross n matrices here. Okay? Because we are saying that we are having also multiplication on this. Now, if you take rectangular matrices of unequal dimensions, you cannot multiply them. You can of course add them, but not multiply them. So for matrices, let's introduce this two notations. M cross n R is the set of M cross n matrices with entries from R. Okay? And this R will be replaced by other sets later. Okay? C or some general field F. Okay? And then, if these two dimensions are the same, we do not write, we do not use more substitutes, we just write in NR. The set of n cross n real matrices. And here we are talking about this one. Okay, so these ones you can add. This is an abelian group under addition, right? Zero, the entire zero matrix is identity of this under addition. Whereas you can also multiply things here. Okay? And there is identity element in this. So it is indeed a monoid under multiplication.
So
yes.
If the field changes, the R in general field,
yes.
so the multiplication, the rule changes, right?
The multiplication, I mean, how do you multiply matrices? That doesn't change. You always multiply matrices like you take, I mean, if their dimensions are compatible, you take one row here and you multiply with the column entries here. And if it is the ith row and jth column, then you just get ijth entry multiply after multiplying this.
But the elements of the matrices are from the F field, in general field.
Yes.
So their multiplication rule changes.
Multiplication rule?
I mean, if there is a
yes, of course, the plus and the star in that field will be something different. But you use that operation in that field to get that ijth entry. So these two are the, what you call, this addition and multiplication in this abelian group. And then what we have is, well, another, I mean, this is not the entire set of, what you call, assumptions. The other one is that star must be distributive over addition. Okay? Distributive over plus. Okay? What does that mean? A star B plus C is equal to A star B plus A star C. Okay. And you don't know whether this is commutative, right? So you also have to write it from the right hand side. B plus C star A is equal to B star A plus C star A. By this we mean, I mean, this is saying that the multiplication is distributive with respect to addition in this field R. Okay. In particular, if this is commutative, we call R a commutative ring. Okay. So, where do we write it? So in particular, all all and everything what we wrote here are examples of rings. A commutative ring is a ring with a commutative operation star. That is where the multiplication is commutative. We call this the addition in the ring R, this the multiplication in the ring R. Note that this addition and multiplication may not be the usual addition and multiplication. It depends on the ring what these things are, plus and star. So a ring with a commutative multiplication is called, or in other words, if this is a commutative monoid, then we call R a commutative ring. Okay. And now, finally, we could define what is a field, on which we will define our vector space. So a field is a commutative ring if such that f star, which is defined to be f minus 0, is an array element under star. Under multiplication. Okay. Well, we are calling it a commutative ring, so this is anyway multiplicative. What more is that this will have multiplicative inverses of all the elements. Okay. So examples of field, we have seen plenty of them, like the reals, the rationals, the complex numbers, and so on. Okay. In fact, you may complain that you are just defining these fields, and these are well known. I mean, we have all seen these fields. Are there any more fields? There are plenty of fields actually. For example, you can. Okay, last time we were talking about this Z modulo, the residue systems, right? So Z modulo Pz, that is the residue system modulo P for any prime P, this forms a field. Okay, we'll see this. Okay. And then, have you seen? I mean, do you know how do you denote the set of polynomials? For example, say real valued polynomials or real polynomials with real coefficients. Excuse me. And if you define it over the reals,
so we can express it as a column vector as well.
A column vector?
A polynomial with real coefficient can be expressed as a column vector.
Yes.
The coefficients in.
We will. I mean, if you define it as a column vector, then actually you are referring it to as a vector space. But you would also like to define multiplication in that, right? And Rx, for example, what do you think? Is it a ring? I mean, what's the most general structure that's on it? A field, a group? Rx is a set of all polynomials with their coefficients. So, yeah. Wonderful. It's a commutative ring. So we can extend it to a field as well. Okay. Just add instead of Rx, take the rational functions. A rational function means that you're dividing a polynomial with another polynomial. Take all of them inside this, okay? And then we denote it by Rx. Okay? That is the set of rational functions, that is polynomials by polynomials with coefficients, and all the polynomials would have coefficients from R. This will give you a field. Okay. Alright? So, I mean, given any field, of course, any field F, I mean, in particular, take that field Rx, and you could now consider polynomial Y with coefficients from here. Okay? And then again, you extend it by taking the rational functions in y with coefficients from Rx. Okay? And you can continue this. Okay? So, in particular, given any field, you have this field of field of rational functions defined on F. Yes.
Can you explain that once again, like the RX?
Yeah, sure. So Rx is the set of polynomials n0 plus a1x plus dot. We are denoting x like that. X an xn such that these ai's, the coefficients, are all reals. Okay, that's Rx. And by Rx we mean sum, the set of f by g such that f and g both are in Rx, g not equal to 0. Okay, so these are examples of fields, and let's end this class with just the definition of this. Yes, Sukrita, tell me.
Also, sir, in the diagram which you have drawn of
Okay, Abelian groups.
yeah. So where you will represent ring in it?
Inside the set of abelian groups, because a ring is an abelian group with some additional structure.
Also commutative ring inside that?
Yes, of course, because it has another concept that the operation is commutative. So in the set of rings, commutative ring, or in the class of rings, commutative ring is a subclass. And then inside that we will put fields. Okay. Yes.
That you told the distributive property, is it a part of ring or is it?
It's a part of ring. I mean, it's defining rings. So rings are not completely defined without this distributive property. So we will have this operation, another operation star, under which it's a monoid, and that operation star should satisfy these two properties. Yes, please.
For the ring, you mentioned that it is an abelian group.
Yes.
So
Abelian group under this.
Yeah. So abelian group is already commutative. It means the ring is already commutative. Why do we need another definition of?
For a commutative ring, well, that's a very good question. It's commutative under addition. Okay, but we do not know whether it's commutative under multiplication. A commutative ring is a ring which is commutative with respect to multiplication as well. So it is commutative both under addition and multiplication. Okay, that's a commutative ring. For example, that happens in all of this, right? Whereas an example of a ring which is not commutative, can you give me? Anybody? Matrices, right? Wonderful. Yeah, because consider the n cross n matrices. You can add them. Addition is commutative there. Okay? But multiplication is, excuse me, this is the board. So addition is commutative in the set of matrices, in the group of matrices, in the ring of matrices, and multiplication is not in general. Okay, A times B, where A and B are matrices, n cross n matrices, is not equal to B times A. Okay, unless this A and B comment, but that's not always true. A and B may not comment. You have seen this perhaps in the earlier class, I hope. Yes.
Sir, but the identity element does not exist within the domain of m cross n matrices in that case.
We said that it's a. When we are defining the ring, we said that we are considering M and R, not M cross M R. That was a general notation. But here we wrote that these matrices, which we mentioned here, are square matrices, because otherwise we cannot even define this star. You cannot multiply two M cross N matrices together unless M and N are equal. Right? Okay, so we are going to define vector spaces. I hope we can proceed. Is there any other questions about the basics? So we can pass it from that part. Or maybe this part. This one was the oldest board.
Sir, why do we exactly need fields when we have commutative loop?
To define vector spaces. Vector spaces are defined over fields, and moreover, in a commutative ring, we do not have the multiplicative inverse of each of the elements. So in commutative ring, all you have is that this operation star is commutative. For example, in all of this, we see that the operation star is commutative. Okay? But nevertheless, it's not necessary that in a commutative ring always an inverse should also exist. Can you give me an example of a commutative ring where inverse doesn't exist?
Q without the negative.
Yes.
Fractions without the negative.
Yes, but more simple example. How would Z? Z, the set of the set of integers. It's an abelian group under addition, and it's a commutative monoid under multiplication, but multiplicative inverse doesn't exist there. Okay. So this is an example of a commutative ring which is not a field, and we do not define vector spaces over there. We define vector spaces over fields. Over that, we define some similar kind of structure. We'll call it modules, which you will learn later if you take up algebra. Okay. And we can do some things that we will do over vector spaces also with the modules. But not all of the things that we do over vector spaces. Okay, so now what is? And we wrote the set of integers as an example of a commutative ring. So if you have not put it down in your copy, please. Vector spaces. What are they? An abelian group. Group V plus say, and for each vector space, we'll define a vector space over a field F. So a vector space should be defined over some field F. Okay, the underlying field of a vector space V. And it is not only an abelian group, but it has this additional structure called scalar multiplication with elements from F. And this satisfies, well, in groups you have seen these two properties: associativity, identity, and inverse, right? So here it's, because I'm drawing analogy to the concept of groups, because the axioms of scalar multiplication, which we are going to write here, has something to do with the first two, associativity and identity. Only the last one was inverse, and instead of that, we will have here distributivity. Okay, and all with respect to multiplication with elements from F. So here, by associativity, we mean that if A and B are two elements in F, and if you multiply a vector V, so you're multiplying a vector V with, say, A star B, and this star is in the field, whereas this one, say, in the vector space. Later we will not distinguish between star and star, we will just write AVV. Okay? But for now, because we are doing it for the first time, let's write in this manner. This is multiplying with the scalar, this vector, and this is the multiplication in the field. Okay? So this one would be the same as A star V star V. Okay. So V star V is an element in V. Okay. So what is a scalar multiplication? The scalar multiplication is like a binary operation, but nevertheless it's not from not from S cross S to S, but F cross V to V. Okay. Scalar multiplication is a map from F cross V to V, and we'll write it as A comma V is going to A star V only for this class. From the next one we will just write AV. Okay. This is, since the concept is new to you, so that's why I am writing it in this manner. And then identity would signify this. Let's use this part of the board because there it might be too clumsy. Associativity you understand, that is you multiply it in the field. It doesn't matter whether you multiply it in the field or you multiply in the vector space. You can do this operation first in the vector space and then multiply from the element of the field, and you get A star V times V, the same thing. Okay. And then this identity thing, what does it mean? Suppose suppose 1 is the identity element of the field. Okay. By 1f, say we denote the multiplied identity of the field, then this times V is going to give you V. Okay. This operation is going to give you feedback. So this is identity, and distributivity just means that A star V plus W. Now V and W are elements in the vector space V. Okay, you are multiplying because it's an abelian group. V plus W is also in V, right? If you multiply with this, you get that A star V plus A star W here, and here also A plus B star V is A star V plus B star W. Okay. So it's just like the scalar multiplication is distributive over addition. Okay. Addition in the vector space, and yeah, also this the scalar multiplication is distributive over the addition in the field as well. So these three are the concepts which the scalar multiplication would satisfy, along with the fact that it is an abelian group. Okay. That's the vector space, and the first examples of vector space are a set of vectors, set of tuples, say across one things, A1 an, all from a field, say R. Okay. So these ones you denote by Rn, right? Or if you take the tuple from C, then you define it with Cn or Qn if you take it from Q, okay, and so on. Also the polynomials of a given degree, say a given degree or less, those will also construct an example of vector space. Okay. And you will also have examples of arbitrary dimensional vector spaces, for example, say functions from reals to reals. Okay. You can add them even we don't know about multiplication here because we're just considering the abelian group structure, but you can add them and you can multiply them with reals to get back other functions. So those are the first examples of vector spaces. We will see them in greater detail in the next class. Today in the afternoon at 4, there is a tutorial in the same class. Please attend this, and there will be a mock test. Okay. From the next tutorial, this test will be evaluated. Thank you.